This is question 14 from the SACE Stage 2 Physics course companion in section 1.4 Relativity. Here we have a 500 kilogram object that's initially stationary and accelerates until it reaches a speed of 1 times 10 to the power of 7 meters per second. First, we need to show that there are negligible relativistic effects for an object moving at that speed. That's fairly straightforward. We just use our Lorentz factor, and if we can substitute our speed into this equation and find it's pretty close to 1, then that means that relativistic effects are negligible. So here, LSB 1 on the square root of 1 times 10 to the power of 7, all on 3 times 10 to the power of 8, all squared, and that comes out pretty close to 1. Part B, we need to work out the change in momentum of the object. So here, the change in speed, it goes from 0 meters per second to 1 times 10 to the power of 7 meters per second. So the initial momentum is 0, the final momentum is easy to calculate. So here, change in momentum is the final, take the initial, which is our 500 times 1 times 10 to the power of 7, take away 0, which ends up being 5.0 times 10 to the power of 9 kilograms meters per second. That was fairly straightforward as well. Now, another 500 kilogram object travels at a speed of 0.85 c. We need to work out the relativistic momentum of this object. This is a little bit more difficult. We need to use our expression for the relativistic momentum, so the Lorentz factor times the mass times the velocity. So first we need to work out the Lorentz factor, then substitute that in. We'll do it all in the one step. So here, 1, take 0.85 c on c all squared, multiplied by 500, multiplied by 0.85 c, so 0.85 times 3 times 10 to the power of 8, and if we substitute that into our calculator, we get 2.42 times 10 to the power of 11 kilograms meters per second. That wasn't so bad. So now the object accelerates until its speed increases by 1 times 10 to the power of 7 meters per second. What we need to do is work out the change in momentum of the object. So first we need to work out the new speed, then the relativistic momentum, and then the change in momentum. So that's 3 things that are required for this part. So here, the final momentum will be given by Lorentz factor times mv again, which do our new calculation. So here, our speed, and we'll do this over here, that our speed goes from 0.85 c plus the 1 times 10 to the power of 7 meters per second, which equals 2.65 times 10 to the power of 8 meters per second. So that's the value that we use in here. So 2.65 times 10 to the power of 8, all on 3 times 10 to the power of 8, all squared, multiplied by the mass, multiplied by our new speed, 2.65 times 10 to the power of 8 meters per second, which if we substitute into our calculator, we get 2.83 times 10 to the power of 11 kilograms meters per second. So that's our final momentum after it's increased its speed. We still need to work out the change in momentum. So here will be the final, take the initial, so our final is 2.83 times 10 to the power of 11, take away 2.42 times 10 to the power of 11, which ends up being 4.1 times 10 to the power of 10 kilograms meters per second. So that was a little bit more complicated. There were three things involved in that. So now what we need to do is use our answers for the change in momentum to work out the force required to change their speed by that amount. So here we're using the relationship F is delta P over delta T. So for the non-relativistic change in momentum, we have our change in momentum as 5 times 10 to the power of 9. So 5 times 10 to the power of 9, and that all occurs in a time period of 1.5 times 10 to the power of 3 seconds. And if we substitute that into our calculator, we get 3.33 times 10 to the power of 6 Newton. So in order to increase the momentum of an object from a stationary object until it reaches a momentum of 5 times 10 to the power of 9 kilograms meters per second, that force is required. For the force required when considering the relativistic effects for the same change in speed, we have our change in momentum is 4.1 times 10 to the power of 10 all over the same time period. And if we substitute that into our calculator, we get 2.73 times 10 to the power of 7 newtons. So here we can see that the force required to change the speed by the same amount in both of these cases is significantly different. So for the classical momentum, the force is by a scale factor of 10 to the power of 6, but if relativistic effects are taken into account, then the force required is a scale factor of times 10 to the power of 7. So finally, why objects are unable to reach the speed of light? We can see here from these two calculations, as the speed approaches the speed of light, the force required to change the speed by the same amount increases significantly, and therefore if an object were to go from some speed below the speed of light to the speed of light, that force would become infinite, and so it's impossible. So we can tie all this together. So as speeds approach the speed of light, each change in speed corresponds to an ever-increasing change in momentum, and therefore ever-increasing force. In momentum and greater forces are required to change the speed by even a small amount. And if we were to reach the speed of light, an infinite force would be required. So for V equals C, and infinite force is required. And there we are, that's this question. That's a fairly complicated question, lots of convoluted little things that need to be done. The first part wasn't so bad with just calculating the Lorentz factor. The second part wasn't so bad working out the change in momentum. It should be something that's fairly familiar from stage 1. However, C, D, and E all require lots of smaller calculations to get the whole thing worked out. So for the relativistic momentum, working out the Lorentz factor, then substituting it into the formula, then getting the correct answer. And then for part D, having to work out the final speed, then repeat all that. It's a long process. But aside from that, it's not too bad. The hardest bit's most likely the algebra and substituting it into your calculator, but the actual questions themselves aren't. aren't too bad after you've got your head around relativistic momentum.